Greetings students. In this video we are going to learn polarization of light and Malus theorem. Polarization and something related to that which we call Malus theorem. It can be called Malus law also, can be called a law also. So let us take a quick glance on what is polarization. We consider a transverse wave, and a transverse wave is a wave which vibrates in the direction perpendicular to the direction of propagation. For example, if you have a wall and a string attached to the wall, and the other end is free to move, and you uh, vibrate or move the string in this direction, then what will happen? You will see a wave that is moving in this direction. It will reflect back and you will get a standing wave. So if you are to consider, if you move the string only once, for example, then you will get a pulse of wave which will travel in this direction. Okay, so this is a transverse wave. Now if you keep moving this string, then you will get a standing wave. Okay, and in which direction or in which plane you are moving the string, in that plane only the string will vibrate. Now it is not necessary that you should be moving the string in only one plane. So you can vibrate this in numerous other planes also. You can vibrate this in this plane, you can vibrate this in this plane also. So you can vibrate the string in many planes possible. And a wave which is restricted to vibrate in only one plane, or a wave that vibrates only in one plane, is called a polarized wave. Okay, so what is a polarized wave? Polarized wave, a wave that vibrates in only a specified plane, vibrates in specified plane. It doesn't vibrate randomly in all planes. That is the point. So speaking of polarization, we have a few devices which we call polaroids, which can filter in some sense unpolarized light into polarized light. So assume that this is the polaroid, this is the device, then what goes as an input is unpolarized light, and what comes out is polarized light. Such a device is called a polaroid. Okay, now how to understand a polaroid? Consider the string uh, example I just gave you. Suppose you have between the wall and the string. Okay, between the wall and the string, somewhere over here, you have a slit. Let me draw the slit. The slit has an opening like this, which is very thin. Okay, and the string goes through this slit like this and reaches the end of the other end, which is tied to the wall. Now this end over here, which was free to be vibrated in any direction, can can now be vibrated only in this direction. Okay, because if any other direction, if you vibrate in this direction for example, then the wave will move and it will collide with the slit in a manner that the slit will not allow the wave to pass through the slit, it pass through itself. So on the other hand, if the vibration is in this direction, then the wave pulse will move to the other side with no hindrance. So such a mechanism, I mean, this is a good explanation or a good analog of how a polaroid will work. Okay, so a polaroid allows only those waves which vibrate in alignment with the direction of the slit. All other waves are filtered out, and hence we have such a mechanism over here. Unpolarized light goes in, so all other waves except this wave are removed out, are allowed to pass. So what we have is on the right hand of the slit you have polarized wave. All waves are polarized. Okay, and on this side you may have unpolarized light. So that is what we have. Second, polarized light, polarized wave is given names, are given names. So if you hear or read something like Y polarized wave, you have to understand that the wave is allowed to vibrate only in the Y direction. Okay, this is the Y. In general, vertical direction is the Y direction, horizontal is the X direction, and you may have the third direction also. Okay. Another name is linearly polarized wave. Linearly polarized wave. Now, why we have this word specially linearly? Because there are other polarized waves also. You have circularly polarized wave also. You have elliptically polarized wave also, if I am not wrong. But circularly polarized wave exist, and what are they is beyond the scope of the syllabus. We ought not learn anything about that. But if you are wondering why there is a special word, then why there is a special word, then we can say that there are other polarized waves also, like linearly waves. You have circularly polarized wave and so on. So yeah, so linearly, the word linearly comes here because you see this line over here. This is like a line, okay, and hence the word linearly. One more word is there for this, is plane polarized. Plane polarized. Okay, so this is also, all three names apply for the same wave that you see over here. Okay, so in the exam, if you encounter such words, don't get confused. This is what they mean. All right, so having understood polarization and polarides, now we can move on to understand malus theorem. Malus theorem or malus law. Now, what does malus tell us is something related to polaroids. Okay, every polaroid has a pass axis. Polaroids have something called pass axis. Pass axis means, for example, the pass axis of this slit is in this direction. This is the pass axis. Okay, uh, it will not allow anything else other than this direction vibration. So that is the pass axis. So every polaroid has a pass axis. So you have to assume, or you have to think of a polaroid which is which works in the same way as we just saw, but here we have, this is a mechanical wave we were talking about. Mechanical wave. Mechanical wave. The string, the vibrations, everything is mechanical. So I mean, we can see the string and so on, but here we are talking about an optical analog. So optical polaroid, this is an optical polaroid. Okay, so light waves, which are also transverse waves, light waves are transverse waves, light waves are transverse waves. So they pass through the polaroid. On the other side you get polarized waves. So unpolarized waves pass through this polaroid over here, and on the other side you get polarized wave. So let this be the axis, pass axis. Let this be the pass axis. Now let us assume that a wave is vibrating in this direction, this orientation. So a wave is moving like this. All waves are vibrating in this orientation, for example. And over here they reach the polaroid, and on the other side, what will come out is a question. So let us try to see this polaroid. Suppose this is your eye. So from this orientation, if you see, the polaroid will look something like this. It will look a rectangular sheet like this. And what you see is, this is the pass axis. This is the pass axis. And this is the incoming wave. Okay. Now, let me give you some idea on what the pass axis and incoming wave, the arrows that I have drawn, actually mean. So here you have these arrows. Okay, so let me just give you a glance on what these arrows mean. So when I draw a blue arrow like this, when I draw a blue arrow like this and say this is a wave, okay, now how do you understand by this uh, ray or line? Yeah, line. Yeah, you call this line. How do you understand this line as a wave? Okay, you understand this in the following manner. This is like the amplitude. This distance is like the amplitude, and the wave is vibrating in this direction. Okay, so when you have electromagnetic waves, what is happening in space? In space you don't see any arrows, you don't see any vectors. So how to understand electromagnetic waves? You consider a certain point in space. You consider a certain point in space. So as the wave passes through this point, the electric field increases in magnitude, then it decreases in magnitude, then it flips the direction, then it decreases in magnitude, becomes 0, and again it repeats. Okay, again it repeats the same thing, increases in direction, and so on. Okay, So what you have in effect is the electric field is oscillating in this direction from 0. Okay, and this is the magnet, this is the amplitude of the wave. So that is how you understand this. Okay, now in this diagram, coming back to this diagram over here, uh, if we assume that this is the incoming amplitude a naught, that is to say this distance is a naught. Okay, then how much amplitude will pass? The amplitude will pass will be a component. If you consider this as the angle theta, a component of a naught will pass through the pass axis. Okay, so how much is this? If you apply cos theta, you will find that x is a naught cos theta. Okay, so the component of amplitude that passes through the polaroid is a naught cos theta. So this is a result that we keep aside to discuss further things. So I'm going to keep this aside and now talk about the intensity. Okay, because when you see light, you don't see light and say, okay, its amplitude is so and so. You see light and say its intensity is so and so, its brightness is so and so. You say, oh, the sun is so bright and the moon is so pleasant, and so on. So what you mean is, I mean, what you are referring to is the brightness. Okay, so we have to correlate amplitude with brightness or intensity. So we have something called intensity of light. Speaking qualitatively, intensity refers roughly to brightness. Okay, brightness. So if you are near a bulb or light, the light appears bright. The intensity is more. If you are away from the light, the intensity is less. The intensity decreases as you go away from the source of light. So this applies to sound waves also. For example, if you are near the speaker, you hear the sound loudly. As you go away from the speaker, the sound intensity decreases. Okay, so that is what we have. So I have to elaborate a quick elaboration I have to give on the intensity before we go back to the malus theorem again. Okay, so as I said, qualitatively speaking, intensity is brightness, and technically speaking, intensity I is power per unit area. Power of whom? Power of the wave delivered. Okay, so suppose this is a torch, okay, and it throws light, and here there is a wall. Okay, because of this torch, let's say a 10-meter square area is illuminated. 10-meter square, and let's say the power of the torch was 100 watt. Okay, 100 watt, that is 100 joules of light energy is given out per second by this torch. Okay, so the intensity at a point on this wall, let's say P, will be, oh, let me call it Q, because P is already used here somewhere. So intensity of a at a point Q on the wall will be equal to the power it receives per unit area. Okay, so the power it receives per unit area will be 100 watt per by 10, which is 10 watt. So 10 watts per meter square. This is the intensity at point Q. Intensity at Q. Okay, so at every point. So here I have taken an area surrounding Q. Okay, so in principle you can have intensity as small power divided by small area. Okay, if you are talking about a point. So this is what intensity is. And it just turns out that intensity is directly proportional to the amplitude square. Okay, uh, I don't have a proof for this right now, and I suppose that this proof again is beyond the scope of the syllabus of 12th grade. So for now, anyway, the textbook also doesn't have this proof. So yeah, so intensity is directly proportional to amplitude square. This is something that you agree or accept to agree for the moment and move forward. So what I can write is I is equal to k amplitude square is equal to where k is some constant of proportionality. Okay, so intensity is some constant multiplied by amplitude square. So our question was how amplitude is related to intensity or brightness. It is related to intensity, sorry, the brightness in the following manner. We have we have intensity directly proportional to amplitude square. Okay, so I is equal to ka square. Okay, and if I put a subscript o, then a has will also get a subscript o. Okay, so this is something that we have now. This x over here is basically the amplitude that comes out. Okay, the amplitude that comes out of the polaroid. So the amplitude that comes out of the polaroid over here is a, and the amplitude that goes in is a naught. Okay, so a naught's component comes out of the polaroid. So this box can be written as a is equal to a naught cos theta. A comes out of the polaroid. Now a is equal to a naught cos theta. A is equal to a naught cos theta can be written as a square is equal to a naught square cos square theta, squaring both the sides. You square both the sides and you get this relation. Now why I have squared both the sides is because you see now I can multiply both the sides by k. Ka square is equal to k amplitude naught square cos square theta. And the benefit of multiplying k on both the sides is that this is now I and this is I naught from this. Okay. So therefore I can write therefore I is equal to I naught, sorry, square near. I is equal to I naught cos square theta. Okay. I is equal to I naught cos square theta. And this equation is nothing but Malus law, Malus theorem. So Malus theorem tells us that the intensity that comes out of the polaroid is given by this equation. It is incoming intensity multiplied by cos square theta. Okay. So this is what we have as Malus theorem. So I hope polarization, polaroids and Malus theorem is clear, and I thank you for your attention.